Okay, yes, students, very good evening, everyone, and welcome once again to OM Institute, your favorite preparation platform for ECEE and for GATE, engineering services, AE exams, and all technical examinations as well. Okay, so as you know, we are having the series on concepts through previous year questions. Control system is the subject we are having. We have had multiple sessions already. Just a second. For GATE, engineering services, AE exams, and all technical. Yeah. Okay, so we have had several sessions like, starting with time response, steady state error, Routh-Hurwitz, root locus, Nyquist plot, Bode plots, etc. And now today we'll discuss, after, having discussed Bode plots and Nyquist plot both, we are going to discuss up the gain margin and the phase margin and the different variety of questions around the gain margin and the phase margin. Okay. Okay. Yes, very good evening, everyone. Come on, everybody, quickly keep on joining. Good evening, Sharma. Good evening, Ramesh. Okay. Right. So let's get moving ahead. Gain margin and phase margin for today. Okay. So this is a regular intro about me. You're aware about that. Now, to dive into the concept, of course, I'll revise some concept as well. Good evening, Satyam. Okay, I'm starting with the question of Nyquist plot. It is a gate question. As you know, this is P by Qs, so all gate questions only we are taking. Okay, the last session only we have discussed Nyquist plot and the concept around encirclements, the formula n equal to P minus Zn, etc. The Nyquist plot of a stable transfer function, okay, of a stable transfer function is shown in the figure. We are interested in the stability of closed loop system. GS may be stable. Okay, GS, that is the forward path gain, may be stable, but I am interested in the stability of closed loop system. Correct. I am interested in the stability of the closed loop system. Good evening, Venkat Shiva. Okay, I am interested in stability of closed loop system. Okay, so now, dear, we know that stability of closed loop system depends on what? Depends on the poles of closed loop transfer function, or we can say that roots of characteristic equation. And as per the Nyquist criteria, the roots of characteristic equation, okay, in RHP, stability depends on the roots of characteristic equation in RHP, and that was represented as Z plus. That was represented as Z plus. Okay, that is represented as Z plus. Okay, where Z plus, where Z plus is given by the formula n equal to P plus minus Z plus. Okay, assuming clockwise Nyquist contour. Nyquist path is not mentioned here. Okay, so let me for a moment assume Nyquist path as the clockwise. The n is given by the formula P plus minus Z plus. Now, when you talk about Z plus as the zeros of characteristic equation, as the roots of characteristic equation, then what is n? N is the number of encirclements of -1, 0. Okay, now this is a common data question, old question. Okay, but to start the concept, I have taken this question. Okay, GATE 2009 DC 2 mark question, common data, 2 questions will be there. The second one will be gain margin and phase margin question. Okay, so have a look into it. Which of the following statement is true? GS is all pass, it has a 0 and right half S plane. Right half plane, it is the impedance of a positive network, it is marginally stable. Now, whether or not it has a 0 in the right half of the S plane, let me use the Nyquist criteria to conclude. Okay, my main focus is gain margin, phase margin. Okay, so I'll give you the answer of this by our previous class concept. Okay, by our previous class concept. So as I'm telling you, see, P plus has the fixed meaning. What is P plus? P plus is equal to the poles of GS or poles of GSHS in RHP. Okay, that is why I use a symbol plus. Plus meaning it's in the positive side, right hand side. Okay, right hand side. Okay, now when I write down the formula n equal to P plus minus Z plus, P plus I already explained you. Okay, and whenever you see the encirclements of 0, 0, okay, whenever you talk about the encirclements of 0, 0, then Z plus is known as zeros of GS in the RHP. That is what we have discussed in detail in the last class. Okay, so if you talk about the encirclement of origin, dear, see, this is the origin, actual origin, 0, 0. Okay, is it encircled by the Nyquist plot? Yes, you see, it is encircled by the given Nyquist plot, and it is encircled in which direction? It is clockwise direction. It is clockwise direction. Okay, so here it is encircled once in the clockwise direction, and for clockwise the sign convention is negative. Okay, the sign convention is negative. So if I put down the value of n, which is -1, is equal to p plus. Now what is p plus, dear? What is p plus? Poles of GS in RHP. Okay, GS is given to you as a stable transfer function, and if there is any transfer function which is stable, it cannot have RHP poles. Okay, so what is clearly mentioned to you is p plus is 0, because in the question they have clearly mentioned that GS is stable. Okay, so I will put down these values. So p plus is 0 minus z plus, and z plus is equal to 1. Now what z plus is this? It is the zeros of GS in the RHP. That clearly means that GS has 1 0 in the right half plane. Option number B is correct for the first one. Okay, this is the first question, and there are two questions. As I told you, this is common data questions. Okay, two questions are there on the same data. Okay, so first GS has a 0 in the right half plane, z plus equal to 1. Okay. Now dear, again let me reuse the formula. Okay, my first question is solved. Again let me reuse the formula here only. Okay, where n is p plus minus z plus. Okay, where p plus means the same only. Okay, but whenever you want, p plus is same, poles of GS in RHP, but whenever you want zeros or roots of characteristic equation in RHP, okay, as we know, characteristic equation means 1 plus GS HS equal to 0. HS is 1 here. So 1 plus GS equal to 0. Okay, so when I want to talk about the roots of 1 plus GS equal to 0, then we had the concept of shifting the origin, and we had the new origin as -1 comma 0. Okay, last class. Okay, -1 comma 0. Okay, now where is -1 comma 0 here? This is -1 comma 0, x-axis point, -1 comma 0. Okay, is it encircled? No, this is outside the plot. This is outside the plot, it is not encircled. Okay, so -1 comma 0, dear, is not encircled. Is not encircled. So the n value is 0. And if I put the n value as 0, in the p plus is also 0. Okay, p plus is 0 minus z plus. So this time z plus is 0. What is this z plus, dear? Which z plus it is? Okay, it is the roots of characteristic equation in RHP. Z plus equal to 0. That means there is no root of characteristic equation in RHP and the system is stable. Okay, the closed loop system. Okay, the closed loop system is stable. The closed loop system is stable. Got it? Now, we know that this system is stable, dear. We know that this closed loop system is stable. Keep listening. Okay, keep listening. Now, where is the -1 comma 0 point? -1 comma 0, because for stability analysis, what is important is the encirclement of -1 comma 0. Where will -1 comma 0 lie? Where will -1 comma 0 lie? -1 comma 0 lies on the negative x-axis. It lies on the negative x-axis, correct? Okay. Now, what is the actual gain of the system of the Nyquist plot, okay, or of the GS on the negative x-axis? It is -0.5. That is why I told you, -1 comma 0 is outside. -1 comma 0 is outside. Okay, because the actual gain is -0.5. If this gain was little more, okay, if I increase this gain, okay, suppose if I multiply by 1.5 times, then it becomes how much? 0.75. Then also -1 comma 0 outside, same answer, stable. Okay, but suppose if I multiply it by, suppose 4 times. If I multiply the gain of the system by 4 times, then what will happen? Then 0.5 into 4 will be 2. Okay, so this point, okay, this point will go up to -2. Okay, the Nyquist plot will be little bit enlarged, and it will cross through this point -2. Okay, direction remaining the same. Now there is one encirclement. Now -1 comma 0 is encircled, and because -1 comma 0 is encircled, clockwise direction only. Okay, so n will be -1. Okay, n will be -1 equal to minus z plus equal to 1. One RHP root in the one RHP characteristic equation root. System is unstable. Okay, so if you, right now the system is stable. Okay, but there is a chance that if you increase the gain of the system after a certain range, it will become unstable. After a certain range, it will become unstable. It will become unstable after a certain range, correct? After a certain range. That means currently system has some margin by which its gain can be increased. That is what is known as gain margin. Okay. Okay, its margin is how much? Maximum you can multiply it by 2 times. 0.5 into 2, 1. Okay, if you increase it beyond that, then encirclement will happen. Okay, if you multiply up to less than 2, it is going to not encircle. Okay, so what is the maximum allowed? Okay, multiplier. Okay, that will be known as the gain margin. Have a look into the standard definition. Okay, because my next question is on gain and phase margin. Okay, I told you common data, second question will be there. Okay, now see. Okay, gain margin. What is the gain margin? It is the margin by which the gain of a stable system, like previous one, system is stable, okay, can be increased before it reaches the point of instability. Okay, what is the point of instability? Okay, what is that point of instability? Minus 1 comma 0. The stability is dependent on the encirclement of minus 1 comma 0, right? Okay, now how much is the margin? How much is the margin? As I told you, as I just explained you can multiply maximum by 2. Okay, because the point of instability crosses through minus 1 comma 0, or means the magnitude here is 1. Okay, magnitude here is 0.5, you can maximum amplify by 2. Okay, that means if the magnitude was suppose m, rather than 0.5, if it was m, you can maximum amplify it by 1 upon m. M into 1 upon m, cancel, answer will be 1. Okay, maximum point it should reach is this point, which is 1. So that means what is the gain margin? What is the maximum multiplier factor? Okay, it is 1 upon the current magnitude. 1 upon this current magnitude. Okay, 1 upon this current magnitude. So 1 upon 0.5. That is why I am telling here the margin is 2. Okay, here the margin is 2. Okay, so listen to me. Okay, so what is the gain margin? It is reciprocal of the magnitude. It is reciprocal of the magnitude. Now, which magnitude I am talking about? I am talking about the magnitude when the Nyquist plot is cutting where? When the Nyquist plot is cutting the negative x-axis, negative real axis. Why negative real axis is important? Because minus 1 comma 0 lies on the negative real axis. Okay, now this frequency is not given up here. Okay, but this frequency, okay, where the Nyquist plot cuts the negative x-axis, will be defined as omega p. Will be defined as what? Will be defined as omega p, which is known as phase crossover frequency. Okay, and the magnitude at phase crossover frequency is how much? 0.5. Minus is the coordinate, but the actual magnitude, distance from origin, is 0.5. So what is the gain margin? Reciprocal of 0.5. Okay, so here it is. Look into this definition. Phase crossover frequency. It is the frequency at which the Nyquist plot intersects the negative real axis. Okay, at which the Nyquist plot intersects the negative real axis. And how do you calculate this? Every time if a question, numeric question is given, you don't have to draw the Nyquist plot. You can solve a question of gain margin or phase margin independently. For gain margin, you need phase crossover frequency. Okay, and at the phase crossover frequency, because you cut the negative x-axis, so what is the phase? Negative x-axis means plus or minus 180 degree. So at this point, okay, at the frequency omega p, angle gj omega p at j omega p is plus or minus 180 degree. Angle gj omega p at j omega g is plus or minus 180 degree, correct? It is plus or minus 180 degree. It is plus or minus 180 degree, right? Okay. Now, commonly the gain margin is also expressed in decibel, okay, because we know, Bode plots analysis will require log scale. So commonly the standard unit of gain margin is expressed in decibel, that is in the log scale, 20 log of this value, 20 log 1 upon mod gj omega p at j omega p. What is this? Mod gj omega p at j omega p, it is the magnitude of, GSHS at the frequency omega p, at the phase crossover frequency. Okay, so if I go back to the previous question, okay, okay, what is the gain margin? Okay, what is the gain margin? It is given by 20 log 1 upon magnitude at omega p. What is the magnitude at omega p? 0.5. 1 upon 0.5 is known as 2. Okay, and log 2 is 20 log 2 will be roughly 6 dB. 20 log 2 will be roughly 6 dB. Okay, so because the next question is talking about, tell me the gain and phase margin. So gain margin is 6 dB. Now let's talk about phase margin. Let's talk about the phase margin. Okay. Hello, Sura. Now, this was gain margin, the margin by which gain of a system can be increased, okay, till it remains stable. I mean, there will be a point after which it reaches some unstable point, unstable zone. Okay. Now, minus 1 comma 0 lies on the negative real axis, correct? But I can say one more thing, minus 1 comma 0 also lies on unit circle. Let's think about a circle. Okay, let us think about a circle. Now let me draw a circle here. Okay, let me draw a circle here. Let me draw a circle here passing through, okay, minus 1 comma 0. Have a look into this rough circle approximately. I'm going to call it as unit circle. I call it as what? I call it as unit circle. Okay. Now what is unit circle? Okay, unit circle is circle having center at 0, 0 and radius equal to 1. So minus 1 comma 0 also lies on the unit circle. Now you see this unit circle, okay, intersects the Nyquist plot, or I can say that the Nyquist plot intersects the unit circle at a particular point. At some particular point. The Nyquist plot intersects the unit circle at a particular point. Okay. Now, because it is unit circle, okay, what is going to happen is, dear, okay, the distance of this point, okay, to this point will be 1 unit, because radius is 1, distance from center to the circumference is 1. Okay, right, is 1. Right. So, the distance up to this point is 1. So, I can say that the magnitude of this point is 1. Okay. Now, what is the phase at this point? Okay. Now, normally, how do we measure the phase? Listen to me carefully. Normally, how do we measure the phase? Okay. So, now let me remove this unit circle. This was just to show you once. Okay, yeah. So firstly, I told you this is some point which is going to be defined as omega g. Let me mention it here. This is some point which is going to be defined as omega g. Okay, omega g, gain crossover point. Okay, gain crossover point. Parallelly, let me show you the definitions also. Okay, like I've shown you gain margin. Now coming to gain crossover frequency, it is the frequency at which Nyquist plot intersects the unit circle. Why unit circle is important? Because minus 1 comma 0 also lies on unit circle. Okay, now at this point, as I'm telling you, it is the frequency at which Nyquist plot intersects the unit circle. So how can we find the frequency? At this point, the magnitude will be equal to 1. Okay, because unit circle means the magnitude will be 1. Distance from center to the circumference is radius, and radius is 1. So mod gj omega g at j omega g will be 1. Mod gj omega g at j omega g will be 1. Okay. So now look into this point. As I'm telling you, this is omega g. Okay. What is the phase of the system at this point? What is the phase of the system at this point? Okay. This, how much is this much of the phase? Okay. This is 90 degree clockwise. See, phase is measured with positive x-axis. Okay. Because I have taken clockwise, smaller angle here will be clockwise. If you go anti-clockwise, it is a larger angle. So let me go clockwise. Okay. The 90 degree clockwise means minus 90 actually. Means minus 90. Okay. Now suppose if I start, in the earlier case what I told you, I was enlarging the Nyquist plot. I was increasing the gain of the system. Okay, now I am changing the phase of the system, and because of the change of phase, okay, the Nyquist plot will also rotate. Suppose if this phase is 90 degree for this point, okay, if it was not 90, if it was 100, okay, if it was 100, then this point goes here. If it was more than this, suppose you keep on increasing the phase and make it 180 degree, what will happen? If you keep on changing the phase of this point and make it 180 degree, then this particular point will come up here. Okay, then this particular point will come up here. Okay, right. And if it is more than 180 degree, then this is going to even again bring the encirclement. It is going to even cross this point. Okay, so at 90 degree change in the phase, I come to 180 degree phase where I come to the point of instability. As I already explained you, point of instability minus 1 comma 0. Okay, so right now the system is stable as we have done the analysis. Okay, I can change the phase of the system by how much? By maximum 90 degree. It is at 90 degree, I change it by 90 degree. Okay, 90 degree clockwise, it becomes 180 degree. It crosses the point of instability. If I change it beyond it, the system is going to become unstable. The system is going to become unstable. So right now, like gain margin, I can say that system also has some margin. Okay, system also has some margin, okay, with respect to the phase. How much you can change the phase of the system? 90-degree clockwise maximum in this case, and that will be known as the phase margin. That will be known as the phase margin. Okay, 90-degree. That will be known as phase margin. Okay, now how do I formulate phase margin? Why it is 90-degree? Okay, why it is 90-degree? Because this angle is 90-degree clockwise. 90-degree clockwise means minus 90. Okay, mathematically it means minus 90. So this, when I add 180-degree to this minus 90-degree, then I get this 90-degree. Okay, then I get this 90-degree. So what is the formula for phase margin? So phase margin, it is the margin by which phase of a stable system can be changed before the system reaches the point of instability, and it is given by the formula as I explained you, 180-degree plus angle Gj omega g at j omega g, and the standard unit of phase margin is considered in degrees. 180-degree plus angle Gj omega g at j omega g. For the previous question, as I told you, it is 90-degree. Okay, so 6 dB was the gain margin, 90 degrees the phase margin, option number C. Okay, now we will come to some questions. This was for explanation. Now we will come to some questions where you are required to calculate gain margin and phase margin by using the methods, by using the procedures. Okay, right. Okay. Normally, Sura, Nyquist plots and both Nyquist and Bode plots are both appropriate. But if you talk about simpler level, okay, Bode approximation is simpler to calculate this. Okay, Sura. Chalo. Now let's come to another question. Okay, this is the definition of gain margin and phase margin. Also some important points like we have seen in this example. Okay, the gain margin and phase margin are both positive. Okay, the system was stable as already noted. Okay, so let's not derive it. Let's write down some important key points. Okay, otherwise we'll not be able to solve any question. Okay, this is a PYQ session more or less. Okay, so for a stable system, both are positive. For unstable, both will be negative. Okay, and for a marginally stable system, both are 0. For a marginally stable system, both are 0. That means both are of the same sign. If system is stable, both positive. If system is unstable, both negative. It cannot be possible that one is positive, one is negative. Never possible. Okay. For two systems, suppose they have the same gain margin. The system which has the more value of phase margin is said to be more stable. Okay, there's a relative comparison. That is why these are also known as relative stability parameters. Okay, suppose if there are two systems having same phase margin, then the system which has more gain margin is called as more stable. Okay, and also there are some more relations, some more shortcuts to assess stability. Okay, as I've defined omega g and omega p, gain crossover and phase crossover frequency. Whenever omega g less than omega p, system will be stable. Omega g greater than omega p, system unstable, and if both are equal, then the system is marginally stable. Okay, then the system is marginally stable. Now let's come to this question, dear. Now let us come to this question. The frequency response of a linear system is provided in the tabular form below. The gain margin and phase margin of the system are how much? Okay, the gain margin and phase margin of the system. Okay, now there is no Nyquist plot or there is no formal, there is no GS transfer function given. Okay, but some frequency response information is given in the form of table. Now if I have a look into the table, okay, what I need here, what all do I need? See, what all do I need? I need the gain margin and phase margin. Gain margin is calculated at which frequency? At phase crossover frequency. What is phase crossover frequency? Phase crossover frequency was defined as the frequency where phase is 180 degree, plus or minus 180 degree. So have a look into it. This point is important here. Where the phase, that is angle, becomes minus 180 degree, okay, is known as the phase crossover point. This corresponds to omega p point, correct? This corresponds to omega p point. So what is the gain margin? So this magnitude will be important, dear. And what is the gain margin then? Gain margin is given by 20 log 1 upon the magnitude at omega p. 20 log 1 upon magnitude at omega p. So what is the magnitude at omega p given? 0.5. Okay, so 20 log, this becomes 20 log 2, and which is 6 decibel, which is 6 dB. Okay, so gain margin is 6 dB. Then I will explain phase margin. But you can stop your answer here. See, gain margin is 6 dB, option number A or B. Gain margin, phase margin are of same sign. One positive, gain margin positive, phase margin negative, never possible. Okay, so we can stop our question here also. Answer is A. It's a gate 11 double E 1 mark question. Answer is A. Because both are of same sign. They cannot be of opposite sign. Okay. Now, okay, but still let me explain you. From this table, how do you talk about phase margin? Okay, so come to this one. Phase margin is calculated at omega g. Omega g, gain crossover frequency. It is the frequency at which the magnitude becomes 1. Mod gj omega becomes 1. Okay, so this will be known as omega g point. Okay, now what is the phase margin? Okay, now then this phase will be important. And what is the phase margin? As I told you, phase margin is known as 180 degree plus angle gj omega g hj omega g, or here it is only g. Okay, 180 degree plus angle gj omega g. Okay, the angle at omega g. So this is the omega g point. Omega g value I don't know, but I know what is that omega g point and what is the phase here, minus 150 degree. So 180 plus minus 150 degree. So phase margin is 30 degree. So the phase margin is 30 degree. Okay, 6 dB and 30 degree. Anyways, I tick marked option number A earlier. It is 6 dB and 30 degree. Option number A. It is 6 dB and 30 degree. Okay. Next question now. Okay, let's move on and start calculating some more expressions. Gate 16 double E 1 mark. 180 or what you are writing? 150, because you see in the table, na? Okay, at the omega g point, what is the phase, Ashok? Minus 150 degree. That is the reason I have taken that value. Okay. Now, a straightforward 1 mark double E question. Okay, only on phase crossover frequency. You don't have to draw any table or any diagram, any Nyquist plot. You can find directly by the formula. Okay, phase crossover frequency. What happens at the phase crossover frequency? So see. Okay, what is the function given to me? Let me convert to the frequency domain, putting s equal to j omega. What is gj omega? 100 is divided by s plus 1, or 1 plus s. S is j omega and whole cube. Okay. Now, what is the angle expression? What is angle gj omega? Now see, numerator is positive real number, so 0 degree. Okay, whenever you have denominator, the phase is in minus. Okay, whenever two complex numbers are divided, phase is subtracted. Okay, what is the phase of x plus j? By tan inverse y by x, tan inverse omega upon 1. Okay, but this factor is repeated 3 times. So tan inverse omega by 1, tan inverse omega by 1, tan inverse omega by 1 will come 3 times. 1 plus j omega into 1 plus j omega into 1 plus j omega. So what is the phase expression? Minus 3 tan inverse omega by 1. Okay. Now, what do I need? I need in the question phase crossover frequency. Okay, what happens at phase crossover frequency? It is the frequency at which angle gj omega p, okay, should be plus or minus 180 degree. Let me choose minus 180 degree because I have the minus expression there. Okay, let me use that angle gj omega expression. So what is the angle gj omega expression? Minus 3 tan inverse omega p is minus 180 degree. Okay, is minus 180 degree. What is tan inverse omega p then? Okay, cancelling by 3, it becomes 60 degree. Tan inverse omega p is 60 degree. So what is the omega p? Okay, it is given by tan 60 degree. And what is tan 60 degree? Is root 3. What is a tan 60 degree, dear? It is equal to root 3. Okay, tan 60 degree is root 3. Okay, so what is the correct answer? Is option number A. Okay, option number A. Correct, Ashok. Option number A. Right. So it's a direct question that we are able to solve, and the answer is option number A, that is equal to the root 3. Okay. Now, dear, if I move towards the next question, forget the next question. For the same question, dear, for the same question, can you tell me what is the gain margin? For the same question, please can you tell me what is the gain margin? Okay, just a second. Tell me the gain margin for the same question. Okay, so now as I'm asking you gain margin also. Okay, yeah, so for previous one, correct answer Ashok and Sharma. Now gain margin. Gain margin is calculated at omega p only. That is why I'm asking you the gain margin. Okay, now what is the gain margin? The gain margin, dear, is given by 20 log of 1 upon magnitude at omega p, 1 upon mod gj omega p. Okay, now what is mod gj omega p? Have a look into it. First of all, what is mod gj omega? This is gj omega. Write down the magnitude of it. The magnitude of 100 is 100. Magnitude of x plus jy is under root x square plus y square. Under root x square plus y square, and then whole cube is there. Whole cube. Okay, so this is like 100 divided by 1 plus omega square whole power can be written as 3 by 2. Under root is power 1 by 2. Correct? Okay, so this is the mod gj omega. Okay, now I want the magnitude at omega p. Okay, so what is the mod gj omega p? Hey, what is this omega p frequency? As calculated, omega p is root 3. Okay, so 100 upon 1 plus omega square, root 3 square will be 3, power 3 by 2. So 100 upon 4 power 3 by 2. Okay, so this should be how much? 4 cube 64, under root of 64, 8. 100 by 8. 100 by 8. Now I will put down the value here. So what is the gain margin? Okay, 20 log 1 upon 100 by 8. Okay, and that is 20 log 8 by 100. That will become how much? 20 log 2, 6. So 3 into 6, 18. And log 100 will be 2 minus 40. So approx minus 22 decibel. Check your answers. Approx minus 22 decibel is the answer. In the form of decibel. This approx minus 22 decibel. That also leads to one important conclusion. What is that conclusion? Okay, minus 22 decibel is the answer. And what is that important conclusion? That the system is going to be unstable. Gain margin negative, system will be unstable. Okay, in form of decibel minus 22. All the previous question was simple, 1 mark. They've only asked the phase crossover omega p, but we have calculated both, not a problem. We have calculated both of them. Right? Correct, dear? Okay. Now, let's come to the next question. Now, the phase margin question. A GATE 2023 IN instrumentation 2 marks question. The phase margin of the system with the open loop transfer function GSHS equal to twice 1 minus S upon 1 plus S whole square. Now, we need the phase margin in this question, NAT question it is, and phase margin is calculated at which frequency? At omega g. Okay, so let me first again convert this function into frequency domain. Putting S equal to j omega, I have gj omega at j omega. Okay, and that is equal to how much? That is twice 1 minus j omega divided by 1 plus j omega whole square, divided by the 1 plus j omega whole square. Correct? Twice of 1 minus j omega is divided by 1 plus j omega whole square. Correct? Right. Now, what is the magnitude function? Let us write down the magnitude function. Okay, so that's going to be twice 1 minus j omega. Magnitude is anyways 1 plus omega square only. X plus jy or x minus jy. Magnitude is under root x square plus y square. Now this is 1 plus j omega. Magnitude is under root 1 plus omega square, but whole square. 1 plus j omega whole square. So one of the term will get cancelled and the magnitude function is 2 upon under root 1 plus omega square. Okay, and what is the phase function? Okay, what is the phase function? What is angle gj omega hj omega? Let us write down angle also. Okay, so numerator 2 is a real number. Come to this one. Okay, come to this one. Tan inverse imaginary part by real part. So tan inverse omega minus omega by 1. Tan inverse minus omega by 1. And then denominator. Whenever you have a denominator term, phase is subtracted. Okay, how much? Tan inverse y by x. So this is tan inverse omega by 1. But again, one more 1 plus j omega. Okay, so 2 times this angle will come. 2 times tan inverse omega by 1. Tan inverse minus y by x is minus tan inverse y by x. Okay, so minus tan inverse omega and minus 2 tan inverse omega. Okay, so what is the overall angle function? Okay, overall this angle is given by minus 3 tan inverse omega. Minus 3 tan inverse omega. Okay, now the question is asking phase margin, and where is the phase margin calculated here? The phase margin is calculated at the omega g. The phase margin is calculated at omega g. So let's start calculating. The phase margin is calculated at omega g. Okay, let's do it then. Okay, let's do it. So let's first come to omega g. What happens at omega g? At omega g, mod gj omega, final definition, mod gj omega hj omega is equal to 1. The magnitude is 1, Nyquist plot crossing the unit circle. Okay, so this function I will take. Okay, 2 upon under root 1 plus omega square. Okay, and this should be equal to 1. At which frequency? Omega g. So let me say this is omega g. So that means what? 1 plus omega g square. Under root 1 plus omega g square is 2. Okay, take the square. So 1 plus omega g square will become 4. And omega g square is equal to 3. Omega g square equal to 3. That means omega is root 3. That means omega is root 3. Okay, omega is root 3. Okay. Omega is root 3. Omega g is root 3. Okay, not omega p, Ashok. Omega g. Now, the question is on phase margin. Okay, the question is on phase margin. So what is the phase margin formula? Phase margin is given by 180 degree plus angle gj omega g hj omega p plus phase at the omega g point. Okay, so this is 180 degree. What is the angle expression here? See, what is the angle expression? Minus 3 tan inverse omega. Okay, minus 3 tan inverse omega. Which omega? At omega g. Now I will put down the value. So this becomes 180 degree minus 3 tan inverse omega g. What is omega g? Is root 3. Okay, so 180 degree. Tan inverse root 3 is 60 degree. So 3 into 60 is 180. 180 minus 180 is 0 degree. 180 minus 180 is 0 degree. What does it mean? Phase margin is 0 degree. What does it mean? We can conclude that the system, as I've already told you some conclusions, we can now conclude that the system is marginally stable for sure. We can say that the system is marginally stable. Okay, let me explain it to you. What I'm trying to tell you is, we can say that the system is marginally stable. Okay. Now, just a small explanation. What is the characteristic equation here? We know that characteristic equation anyways is given by 1 plus GSHS equal to 0. 1 plus GSHS, 1 plus twice of 1 minus S divided by 1 plus S whole square equal to 0. So now that is S square plus 2S plus 1 plus 2 minus 2S is 0. Now see, 2S cancel. S square plus 3 equal to 0. What are the roots of characteristic equation? S square is minus 3. Okay, if I want to calculate the roots of characteristic equation, so S is plus minus j root 3. Okay, the roots are pure imaginary, and that happens for marginally stable case only. Whenever the roots of the system are pure imaginary pair, you have an imaginary pair of roots and nothing on the RHP. Okay, system is marginally stable as done by the basic analysis also. The system is marginally stable. The system is marginally stable. Correct. The system is marginally stable. Okay, fine. Okay, as you know, as I just told you, we don't have to prove it, but just I'm telling you, phase margin was 0, so system is marginally stable. The system is marginally stable. Okay, now let me show you one question here actually. Let's learn some other cases also. Let's come to this question. Although old gate question, but something to be learned. Okay. Yeah, you can check directly also by characteristic equation, but the point is, Sharma, okay, my point is, here by chance it is marginally stable. Okay, s square plus 3 equal to 0. Okay, if it was not marginally stable, suppose. Okay, that's why I don't suggest to check it directly, because we don't know what is the result in the beginning. If it was suppose stable, you solve some characteristic equation by the stability analysis by Rauth-Hurwitz, you can say it is stable. Okay, but by that procedure, okay, can you say how much is the phase margin? Actual question was phase margin. Okay, not on commenting stability. Actual question was phase margin. I am just linking it to the concept of stability. Okay, na? So in the beginning, we don't know. Suppose it turned out to be stable. You've done some characteristic equation or RH efforts you have done, and you got the system stable. But can it tell the phase margin? No, RH cannot tell any relative stability criteria. So again, you have to restart the problem. Okay. Now old gate question, but something to be learned here. Phase margin of the system with open loop transfer function GSHS equal to 1 minus S upon 1 plus S into 2 plus S. Okay. Upon 1 plus S into 2 plus S. Okay, chalo. So the let's again phase margin, and phase margin is calculated where? The phase margin is calculated at omega g. Okay, so let me again convert it to the frequency function. Okay, gj omega hj omega. What is gj omega hj omega? 1 minus j omega divide by 1 plus j omega into 2 plus j omega into 2 plus j omega. 1 minus j omega upon 1 plus j omega into 2 plus j omega. Correct. Let's take this function. Okay, let's take this function. Now, what is the magnitude part? Mod gj omega hj omega. Again, see now, dear, magnitude of 1 minus j omega and 1 plus j omega is same, na? Under root 1 plus omega square. So that will be cancelled. For magnitude wise, it will be cancelled. So I only have 1 upon under root 2 square plus omega square, that is 4 plus omega square. Okay, what is the angle expression? What is the angle gj omega hj omega? What is the angle gj omega hj omega? So angle tan inverse y by x minus omega by 1. Denominator, subtract the phase. Tan inverse omega by 1. Again denominator term, okay, so minus tan inverse y by x omega by 2. Tan inverse minus omega by 1 minus y by x minus tan inverse y by x. So this becomes minus tan inverse omega, again minus tan inverse omega. Okay, so minus 2 tan inverse omega. Okay, minus tan inverse of omega by 2. Minus tan inverse of omega by 2. Minus tan inverse omega by 2. Okay, dear. Now, how much is omega g? Okay, the first calculation is omega g. And at omega g, how do we find omega g? Mod gj omega hj omega equal to 1. Mod gj omega hj omega is equal to 1. Correct? Now, what is that magnitude function? 1 upon 4 plus omega g square equal to 1. Okay, this means 4 plus omega g square is also equal to 1. What is omega g square? Is minus 3. So omega g square is minus 3. What is omega g? Frequency. The omega frequency can't be imaginary. Okay, so this does not have any real solution. There is no real solution to it. Okay, that means there is no omega g. Okay, there is no gain crossover frequency. There is no frequency at which the Nyquist plot will intersect the unit circle. There is no frequency at which the Nyquist plot is going to intersect the unit circle, you know, at which the Nyquist plot is going to intersect the unit circle. There is no such frequency. There is no such frequency. Right? There is no such frequency. Okay. There is no omega g. Now, what does it mean? What does it basically mean? Okay, if I just do a rough analysis here, not just to explain you once, if I do a rough analysis here, see, the magnitude is 1 upon under root 4 plus omega square. Okay, the magnitude is 1 upon under root 4 plus omega square. Magnitude part was known to me. Okay, and see, if I take omega 0, dear, if I take omega 0, so tan inverse 0, tan inverse 0, 0 degree phase. 0 degree means positive x-axis. At omega equal to 0, 1 upon under root 4, 1 by 2. And if omega, if I take infinity, okay, so tan inverse infinity 90, so 2 into 90 and another 90. Okay, that will be how much? 270 degree. Am I correct? 270 degree. And at omega equal to infinity, magnitude will be 1 upon infinity, which is 0, minus 270 degree. Okay, so minus 270 degree will take me here. Okay, so see, at omega g, at infinity, how much is the phase I calculated? 270. Okay, 270, 90, 90, 90, minus 270, that is why I'm going clockwise. But what is the magnitude? Okay, 1 upon infinity, 0. I'll just show you these calculations here. Okay, I'll write down these calculations here also. What is mod gj omega p hj omega g is 1 upon under root 4 plus omega g square. And what is angle gj omega g hj omega g? Okay, that is minus 2 tan inverse omega. Okay, what is angle gj omega hj omega? General expression. Okay, and this was having minus tan inverse omega by 2. Okay, Achha, also you can see that because it is having omega g square na, in the denominator, square is always positive. 4 plus, that means this factor is always greater than 4. Okay, so when you take under root, it is greater than 2. That means denominator is always greater than 2, means greater than 1 also. So if the denominator is greater than numerator, answer is less than 1. Magnitude is always less than 1. Okay, then I was showing you some values. Okay, if I take omega equal to 0, if I take 0, what is the magnitude I get? 1 by 2. And what is the angle I get? 0 degree. If I take omega infinity, the magnitude that I get is 1 upon infinity 0. And the angle I get is minus 270 degree. Okay, minus 270 degree. That is what I was trying to tell you. Minus means clockwise. So clockwise 270. Okay, but how much magnitude? 0 magnitude. 0 magnitude means origin. Okay, means origin. Okay, so at origin, when the frequency is infinity, I'll be at origin. And when the frequency is 0, I will be on the x-axis. Okay, which how much magnitude? When the frequency is 0, okay, I'll be on the x-axis. Okay, with the magnitude equal to 1 by 2. Okay, so something of this kind, approximately the Nyquist plot, polar plot will be there. Okay, approximately of this kind. Okay, this is 1 by 2 comma 0 point. This corresponds to, let me mark it. This corresponds to omega equal to 0. Just for one time explanation, keep listening. And this point corresponds to omega equal to infinity. Right? Magnitude is always less than 1. That means whatever is this point, it will have magnitude less than 1. And even whatever is the point, magnitude will be less than 1. Okay. Because this is less than 1, minus 1 comma 0 is definitely outside. Okay. Now, what was the concept of phase margin? See, why I don't get omega g? Phase margin is calculated at omega g. The calculations show that there is no omega g. Calculations show that there is no omega g. The calculations have clearly shown you that there is no omega g, correct? Okay, why there is no omega g? Because the Nyquist plot, okay, this is only the polar plot part actually, okay, but even if you take the mirror image and complete, it can never cross the unit circle. Where is my unit circle? See, unit circle crosses through -1, 0. It will have radius equal to 1. This is what my unit circle is. Okay, this is what my unit circle is. So what I can say that the Nyquist plot never intersects. It never intersects unit circle. Okay, that is why you don't get any omega g, because as per the basic fundamental, omega g is the frequency at which the Nyquist plot intersects the unit circle. So hence we don't get any omega g by the calculations also. We have to stick to the formula only. Okay, but what happens when there is no omega g? Just an explanation I am presenting. Okay, so Nyquist plot never intersects unit circle. Now, what was the concept? Okay, of phase margin? Okay, it is the margin by which phase of a stable system can be increased, can be changed. Okay, before it reaches the point of instability. Okay, so now tell me, how much can you rotate? Even if I draw the Nyquist plot by taking the mirror image of the polar plot about the x-axis, about the positive x-axis. Now, how much you can rotate this plot? By how much you can rotate the plot, okay, before it reaches -1, 0. Because the magnitude is always less than 1. The magnitude is guaranteed less than 1. How much you can rotate? Even if you keep rotating infinite number of times, it never crosses -1, 0. Okay. It never crosses -1, 0. Okay, and that leads to the idea that, okay, the phase margin, okay, the margin by which you can change the phase, by which you can rotate, is infinite times. Okay, because even if you keep rotating any number of times, it cannot cross this point, okay, which is the critical point of stability in the Nyquist plot theory, -1, 0. Okay, so what is the answer? Dear, whenever there is no omega g, it is always the answer that you can take, phase margin equal to infinity. Correct answer is option number D. As I've explained you through the complete Nyquist plot analysis, answer is infinity. Option number D. Answer is infinity. That is option number D. Okay. Okay, so that means, let me place down some important points here. Okay, like one example I've explained. Number one, okay, if there is no real omega g, then what is the conclusion we have found? The phase margin will be infinity. Okay, next you should remember some more conclusions I will add. If omega p, phase crossover frequency, tends to infinity, then the gain margin will also be infinity. Okay, then third one, if omega p is 0, okay, if omega p is 0, okay, then this is an exception case, okay, then don't find gain margin, okay, by formula. The formula fails here, okay. So then how do you have to solve? You have to solve by characteristic equation, or okay, solve by characteristic equation, or sketch the Nyquist plot. This is one exception. Okay, this is more like an exception. Point number 3 is more like an exception. The formula of gain margin will not be applicable if the omega p is 0. if the omega p is 0. Just you should know by chance if such question comes. Normally what type of questions you are getting recent year I have shown you, but if such cases come you should be aware. Okay, if omega p is 0, phase crossover frequency is 0, then don't find the GM by formula. It may give you incorrect result. It's not trustworthy. So solve by directly sketching the Nyquist plot or by characteristic equation analysis. Okay, or by the characteristic equation analysis. Okay. Have a look into this question. In the feedback system shown below, GS equal to 1 upon S plus 1, S plus 2, S plus 3. What is the positive value of K for which the gain margin of the loop is exactly 0 dB and the phase margin of the loop is exactly 0 degree? Okay. Now dear, this question looks like calculations on gain margin and phase margin, equating the gain margin to 0 dB and phase margin to 0 degree. But no, it is not at all a question on gain margin, phase margin calculation. Okay, it's only testing your concept. What is the value of K for which gain margin of the system is exactly 0 dB and the phase margin of the system is 0 degree? This concludes that the system is marginally stable. This concludes that the system is marginally stable. So question is indirectly asking what is the value, positive value of K for which the system is marginally stable. Okay, so what is the value of K for the system to be a marginally stable? Okay, by RH criteria. This can be solved by RH. RH. Okay, if not RH, okay, it's going to be cubic shortcut because it's a cubic equation here. Okay, what is the characteristic equation? Chalo, let me do it very quickly. So what is the characteristic equation? 1 plus GS HS equal to 0. 1 plus 1 upon S plus 1. S plus 2. S plus 3 equal to 0. So solving this, I am going to get S cube plus 1 plus 2 plus 3, 6S square. Okay, so now characteristic equation will be 1 plus KGS actually. 1 plus KGS. This is only GS given. So 1 plus K into this factor. Okay, now yeah, then I will have how much? 5, 6, 11S. Then 1 into 2 into 3, 6 plus K equal to 0. 6 from here and K is there already. Okay. For the system to be marginally stable, what was the condition? What is the cubic equation shortcut? What is the cubic equation shortcut? Okay, the product of inner terms equal to product of outer. Inner equal to outer. Okay. BC equal to AD. Okay, that means 6 into 11 will be equal to 1 into 6 plus K. Okay, so 6 plus K is 66. So K is 60. This question is more like a Routh-Hurwitz question rather than a gain margin, phase margin. Only thing is you should know that the gain margin 0 dB and phase margin 0 degree signifies marginally stable. I repeat, both positive, stable system, both negative, unstable system, both 0, marginally stable. As I've told you in the beginning and we have seen in one example also. Okay. This is what it is. Got it, dear? Sure. K equal to 60. The answer is 60. Okay. The answer is 60. Okay. Next question then. Let me first take you towards a question. Okay, where sometimes the exponential function is coming. Have a look into it. Okay, the open loop transfer function of a unity feedback system is given to you. GS equal to pi e power minus 0.25 S upon S. In the GS plane, the Nyquist plot of GS passes through negative real axis at which point? Now see, this is one of the very rare instances where question has exactly repeated. Some words may be here and there, but data is also same. Okay, data is also same. This was earlier in GATE 2005 EE2 marks, repeated for GATE 19 in EC. That is why I keep telling you, okay, that whatever your branch is, but for the common subjects, you should solve the previous year questions of EC, EE, whatever your branch is. But you should solve for all three, EC, EE, not because of repetition. This is still a rare event, but because you get to learn a lot. You get to learn a lot. Okay. So this was there in gate 5 2 marks doubly, repeated in gate 19 1 mark EC. Okay, now, okay, the Nyquist plot, the question is Nyquist plot of GS passes through negative real axis. Okay, at which point? Now, whenever the Nyquist plot crosses negative real axis at the point, okay, that point is known as which point? Omega p point. Okay, you don't have to draw the Nyquist plot, don't worry. It is on omega p point. It is on omega p point, okay? So let's solve. What is the Gj omega? Let me convert to the frequency domain. Gj omega pi e power minus exponential function is there. The transportation lag e power minus 0.25 j omega is divided by j omega divided by s. I put s equal to j omega, okay? S equal to j omega. Now, what is the magnitude mod Gj omega? The magnitude will be pi. Magnitude of e power j theta is always 1 divided by j omega, magnitude is omega. So magnitude function pi by omega. Angle function, angle Gj omega, pi is positive real number. E power j theta, theta is the phase. What is the theta? Minus 0.25 omega. What is the theta? Minus 0.25 omega. Okay, but in the e power j theta, theta is known as what? Theta is known as the phase in radians. This is the phase in radians. Okay, so either you convert to degree or you write down every term in radian. The unit should be same. Okay, now denominator. Okay, j omega pure imaginary. Okay, 90 degree. Denominator we subtract and j omega pure imaginary to 90 degree. But this should not be written as 90 degree. Either you convert this to degree or you convert this to radian. So let me write down both in radian. Minus 0.25 omega and 90 degree we know simply is pi by 2. So minus pi by 2 I have written here. Okay. Now, as I told you, what is the first thing we need? Okay, the question is asking omega p point. Okay, so what happens at omega p? What happens at omega p? At omega p, the angle Gj omega p will be minus 180 degree or minus pi. Everything I am writing in radian. So, minus 0.25 omega p minus pi by 2 is minus pi. Okay, so 0.25 omega will be how much? Pi minus pi by 2, which is pi by 2. Okay, so what is going to be omega p? This is like 1 by 4, sending there, it becomes 2 pi. Becomes there 2 pi. Omega p is 2 pi. Okay, but the Nyquist plot passes through negative real axis at which point? Okay, so what is the magnitude at the omega p? Okay, the omega p frequency is known 2 pi. Okay, so at omega p, what is the magnitude? Mod Gj omega p will be, the magnitude is pi by omega. Pi by omega p. Omega p is 2 pi. So pi by 2 pi, 1 by 2. What is the magnitude? 1 by 2. Okay, that means omega p is the point here where the Nyquist plot cuts the negative real axis. Okay, and the magnitude means distance from origin should be 1 by 2. Distance of this point from origin should be 1 by 2. So what is this point? Because it is on negative x-axis, coordinate will be minus 1 by 2 comma 0. Okay, in the coordinate form it is minus 1 by 2 comma 0. That is option number A. Minus 0.5 comma 0 or J0 in the complex form. Okay, answer is option number A. Answer is option number A, as seen here. If they asked you the gain margin, suppose if they asked you the gain margin, so then we know what is the gain margin. Okay, 20 log 1 upon mod Gj omega p. 20 log 1 upon mod Gj omega p. So that becomes how much? 20 log 2, which will be 6 dB. If they asked you the gain margin of the question. Okay, so then it is 6 dB. Right now they asked you that point where the Nyquist plot cuts the negative real axis. Okay, minus 0.5 comma 0. Okay, minus 0.5 comma 0. Yes, Sharma, correct. Okay, Vikram, we'll plan. We'll plan for state space also. Okay. Now, dear, moving ahead to the next question. Yeah. Chalo. Next one. Another good question here. GATE 18 EC 2 marks. Okay, with reference to Bode plots it is. With reference to Bode plots. The figure below shows the Bode magnitude and phase plots of a stable transfer function GS. Okay, GS, the open loop transfer function GS is stable. Okay. Consider the negative unity feedback configuration with gain K in the feed forward path. So I've taken another gain K in the feed forward path. The closed loop system is stable for K less than K naught. What is the maximum value of K naught? Okay, what is such value of K naught? Maximum value of K naught. Now understand this question carefully. Okay, what is the figure shows the Bode plot of GS. Bode plot of GS, mod GJ omega, angle GJ omega. Bode plots, as we have learned earlier also, it has two parts, magnitude plot and a phase plot. Okay, have a look into this. The magnitude plot and the phase plot. Now dear, from the phase plot, look into this very carefully. From the phase plot, okay, there is one phase which is minus 180 degree, and we know the importance of minus 180 degree. We know the importance of minus 180 degree. Minus 180 degree, okay, when the phase becomes minus 180 degree, that frequency is known as omega p. So this is omega p point. So on the omega axis, what is the omega is not given, but yeah, definitely corresponding to this point, this is the omega scale. So this is omega p. So this is omega p. Same line has been marked. This is the phase plot. This is the magnitude plot. Like we have solved some questions under tabular format. Okay. From the table, we don't know what is omega p, but wherever phase is minus 180, there it is my omega p point, and then we check the magnitude. Okay, now what is the magnitude here? It is given in decibel. Okay, it is given in decibel. Okay, so let's come to this point. Okay, now this is mod GJ omega in decibel. In decibel, that means 20 log mod GJ omega. Okay, at which frequency? Omega p is 20. Is given to you as 20 dB because it is decibel. And how do you express magnitude in decibel? 20 log mod GJ omega. Whatever they write here, but you should know your concept. How do you express in decibel? It is not mod GJ omega. Decibel means 20 log magnitude is the decibel answer. Okay. Now dear, what is the gain margin? At omega p we find the gain margin. Na? What is the gain margin definition? Okay, 20 log 1 upon mod GJ omega p. Correct. The gain margin definition is 20 log 1 upon mod GJ omega p. But what is log 1 by x? Minus log x. Okay, so it becomes minus 20 log mod GJ omega p. Okay, log 1 by x is minus log x. Okay, so minus 20 log mod GJ omega p and 20 log mod GJ omega p is 20. So minus 20 log mod GJ omega p is minus 20. That means gain margin of the system is negative. Okay, so the system, which system? Closed loop system is unstable. Without K, this is the question without K, okay? I've taken only GS. Which closed loop system? If I'm telling you closed loop system, it means this closed loop system. This closed loop system is unstable. This closed loop system is unstable, right? This closed loop system is unstable. No, Ashok, we can't get any omega g value here. Okay, this closed loop system is unstable. Okay, that is why now consider the unity negative feedback configuration with gain K. Okay, I have not taken any gain K right now. Okay. Okay, but with gain K, how we are pointing omega p, Sharma? See, omega p, what is omega p? Omega p is the frequency at which the phase of the system is minus 180 degree, na? Okay, so this is the phase plot given to you. See, this is the phase minus 180 degree. Okay, this is the omega p. I don't know what is the omega p, and okay, not required also. But this frequency on the x-axis is the omega p frequency. And same frequency has been taken in the magnitude plot also. Okay, so we also have the information on 20 log mod GJ omega p, and that is how we got the gain margin. Hope it is clear to all now. Okay, so now dear, now with the gain K in the feed forward path, if I include the gain K in the feed forward path, okay, another gain K, if there was only GS, then the closed loop system was turning out to be unstable. Okay, now with the gain K, okay, what is your open loop transfer function? Okay, Now let's say your open loop transfer function is G1s, because anyways unity feedback is there. Okay, anyways the unity feedback is there. G1s is suppose KGS. Okay, KGS. Because they are in cascade, the gains are multiplied. Okay, it is KGS. Okay, so dear, if I convert into frequency domain, what is G1 j omega? It is KG j omega. Okay, and what is angle? G1 j omega. This K is not going to affect angle. It's a positive real number. K, so angle will be same. Angle G j omega. Angle G1 j omega is angle G j omega. Okay, so because the angle plot, the phase plot is going to be same. Because the phase plot is going to be same, the same omega p will be obtained. Okay, what we can say that there is no change in the omega p, same omega p. But magnitude is changed, so gain margin can change. Okay, now what is the gain margin? Gain margin is given by 20 log 1 upon, yeah, let me write down in the minus form only. Minus 20 log mod G1 j omega p. Okay, this is the magnitude to be used now. Okay, this is the magnitude. Angle is same. Okay, but magnitude mod of G1 j omega will be K times mod of G j omega. So let me put down this value. The gain margin is now minus 20 log K into mod G j omega. Okay, now what is log A into B? Is log of A plus log of B. We can split this. Okay, so gain margin is now minus 20. Log A into B is log A plus log B. So log K, and then again minus 20 log mod G j omega. Minus 20 log K, minus 20 log mod G j omega. Okay, yes, Anil, I'm planning that also for EMF also. Okay, 20 log mod G j omega, and because it is gain margin, it is calculated at omega p. So dear, as I have shown you, what is 20 log mod G j omega p is 20. Okay, so gain margin now becomes minus 20 log omega minus 20. Okay, this much value, as I've already told you earlier, this much value is 20. I've written it earlier. This much value is 20. So now with the gain K in the feed forward path, gain margin is minus 20 log K minus 20. Okay, and you want the system to be stable now. Okay, you want the system to be now stable at least. So what is done for stability? For stability, gain margin must be positive. Originally it was unstable, but I want to make it stable with the gain K included in the forward path. Okay, so the gain margin minus 20 log K minus 20 must be positive. So this means that 20 log K should be less than minus 20. Okay, that means log K should be less than 20 cancelled minus 1. Okay, K should be less than 10 power minus 1, removing the log, taking the exponent on the other side, 10 power minus 1, or K is less than 10 power minus 1 means 0.1. Okay, so K less than K naught. What is that K naught? 0.1. In the question also they are telling the system is stable for K less than K naught. Okay, we have got that the system is stable for K less than 0.1. So what is that K naught? It is 0.1, correct? That is 0.1. This is a good question. Gain margin analysis using the Bode plots. Gain margin analysis using the Bode plots. Okay. Ask me if you have any doubts. Let me now take you towards here a current 2024, a current year 2024 EE 2 marks question. EE 2 marks question. Have a look into it. Good question here. Consider the stable closed loop system shown in the figure. Okay, the closed loop system is also stable. They have clearly mentioned. Okay, the magnitude and phase values of frequency response of GS. Okay, so this is the magnitude and phase information of GS are given in the table. What is the value of the gain Ki? Okay, which should be positive. Gain Ki for a 50-degree phase margin. What is Ki for a 50-degree phase margin? Okay. But our system in the forward part doesn't only have GS information, tabular information is on GS. Okay, but The actual open loop transfer function is Ki by S into Gs. Ki by S into Gs, right? Okay, so what is the actual open loop transfer function? Suppose I call it as G1S, and that is again product. These two are cascaded to Ki by S into Gs, correct? Let me convert to the frequency domain. So G1 J omega is Ki Gj omega divided by J omega. Okay, divided by J omega. Okay, so what is the magnitude and phase expression? Okay, the absolute magnitude will become, okay, Ki into mod of Gj omega divided by J omega, magnitude is omega. What is the angle part? Angle G1 J omega will be, Ki is positive real number, so 0. Then it will be angle of G J omega, denominator minus, denominator is pure imaginary, so the angle is 90 degree. Okay, now the question is telling you that what should be Ki to achieve a phase margin of 50 degree. Okay, for a 50 degree phase margin, that is given. Okay, what is phase margin? Okay, 180 degree plus angle G1 J omega, phase of open loop transfer function. This is the complete open loop transfer function. This must be 50 degree. Okay, that means 180 degree plus what is angle G1 J omega? Put down this formula now. Okay, so this is angle Gj omega minus 90 degree is 50 degree. So this means angle Gj omega will be how much? This is 90, 50 minus 90 minus 40 degree. Now angle Gj omega should be minus 40 degree. Okay, the phase and magnitude information of G is given in the table. So minus 40 degree, this is important. Okay, this corresponds, okay, this omega, okay, where is the phase margin calculated? At actually omega G. Okay, at actually omega G. Okay, so at omega G, phase should be minus 40 degree for G function. Okay, this is minus 40 degree. That means this is omega G point here. This is the omega G point. This is omega G point. Okay, omega G point. Okay, now what happens at omega G, dear? Okay, now next analysis, what happens at omega G? At omega G, magnitude, whose magnitude? The complete open loop transfer function. Okay, the magnitude mod of G1 omega should be 1. Mod of G1 J omega should be 1. Now what is mod G1 J omega? Put down this expression. Okay, it is Ki into mod of Gj omega G divided by omega G. This should be equal to 1. Okay, now what is that omega G? This is the omega G point, and hence this is omega G. Okay, so if I have told you that angle Gj omega G is minus 40 degree, in this question, even the frequency is given, and that frequency is 0.5. This frequency is 0.5. Okay, so that means Ki. Now what is the magnitude of this function at 0.5? What is given to you? See, I'll do some separate calculation. At omega G, which is 0.5, in the table, what is given to you is the decibel value actually, minus 7. Magnitude is given in decibel. Okay, magnitude has been given in decibel, minus 7. Okay, whose magnitude? This is the frequency response of G. Okay, so what I can say, 20 log, okay, 20 log of mod Gj omega G is given to you as 7 dB. 7 or minus 7? Minus 7 is given as minus 7 decibel. Okay, so from here, okay, what is the actual absolute magnitude? Okay, so first to eliminate log, I will take 10 power of what? 7 by 20, minus 7 by 20, divide 20 and then take the 10 power. Okay, this calculation can be done using calculator. 0.446 or approximately 0.45. Okay, so I'll put down these values here. So dear, Ki is multiplied by mod Gj omega G 0.45 divided by omega G was 0.5, should be 1. So what is the value of Ki? It is 0.5 upon 0.45, which if I cancel, should be 10.9. So approximately 1.11. Approximately 1.11 is the answer. Option, no, it's a NAT question. Okay, rounded off to 2 decimal place. Approximately 1.11 is my answer. Good question again here. Good question here. Okay. Okay, it's like some function g has given, okay, with the pi controller. What is this? This corresponds to a, okay, the integral controller, not the pi, it's an integral controller based case. It's cascaded, it has been cascaded with the integral controller case. No, Sharma. This is what is the method. See, it may take around 2 to 3 minutes, I agree, but there are several questions which are done in seconds also. So there has to be, that balancing. That balancing. I told you it's a good question. When I say good question means yes, of course, normally exam also with practice you can take 2 to 3 minutes. That's okay. Okay. If you have good practice, if you're quick in calculation, it can be done in 2 minutes around. Okay, let's count 3 also, but that's okay. There is a balance. Some questions are way easy also. So it's always there. Some questions are there which take little bit of time. That balance is always maintained. Okay. That balance is also maintained. Okay, dear. So like always, I'll share you the PDF of this session in my Telegram group. Okay, you can be connected in my Telegram group with this ID mentioned. Okay, and PDF always will have a password protection, because those who watch the session, they only require the PDF, and if you watch the session, you have the password. So today's password based on what I think is margin, gain margin, face margin. So today's password is margin. Everything in small, MARGIN. Please note down the password for the PDF which will be shared in my Telegram group. If you are not connected in the Telegram, you can be joining there. Every other previous session PDF I've already shared, like Nyquist plot, Bode plots, and root locus, and all those are shared. Okay. Aptitude, Sharma, not tomorrow, on Sunday. Aptitude we are having Sunday to Sunday, na? Okay, so it will be Sunday, and the topic for this Sunday will be, exponents and logarithm. The questions, okay, the tricky questions on property of logarithm, we'll see that. Okay, the exponents and logarithm will be covered this Sunday. Okay, dear. Chalo, that's it. Bye bye. Thank you. Stay safe and take care. Okay, see you now on Sunday with the general aptitude practice dose on the exponents and log.